Okay, so this time we're doing sci-fi, and we're specifically talking about optimize and all of the things that optimize has, specifically fsolve, right? That was the thing for finding roots of equations or systems of equations, non-linear equations, I should say, because you already knew from sci-fi.lineal how to do solving a linear system of equations. And then, did we already do that? Did we already do that? No, that's next time. Sci-fi.lineal. We didn't do that yet. We did. Okay. So before you learned how to solve matrix equations. If you have, AX as B, where A is a matrix and X is a column matrix, you could say, or a vector, you might say. You learned how to solve linear equations like this previously. It's not too important for this class, but now we'll be learning to solve nonlinear equations. So if I've got ax squared plus by squared plus cx plus dy equals 0, and then I've got another one, ex squared plus fy squared equals 10. Something like this. This is a nonlinear system of equations. I've got x squared and y squared terms. I've also got a system. I've got more than one equation. I have to find the x and y that solves these two things simultaneously. So that's what fsolve is for. And we also learned about the FGS method, I think is what it was called. This was just a particular scheme for optimizing. It means finding, I think typically, if you've got a curve or something like that, you've got a function, find the minimum. Not necessarily where it intersects 0. That's what fsolve is for. I want you to find the minimum. And then I told you, instead of using this, there's one function that does it all. Optimize. Or excuse me, minimize was the function. Right? Minimize. And this, so BFGS, this is a particular scheme, a particular method for finding the minimum. Like Newton's method is a scheme, right? This is a particular scheme for doing that. Optimizes or minimizes an interface that allows you to access all of SciPy's methods for doing the minimization, not just the BFGS method. And so the old version was that there were separate functions for each of these different routines. We want to use the minimize interface to all of them. So it's just a little bit easier to remember one word, minimize, than to remember all the separate functions named. And then you can go to the minimize documentation if you want to switch the method that you use to do it. So that's what we learned about. What questions do you have? First of all, conceptually, do you remember Newton's method from one of the early assignments? Hopefully you all did that assignment on the math track. You implemented Newton's method, so you understand how that works. Newton's method for minimization is very similar. It's just you add the second derivative information in there. The videos would explain how that works. What questions do you have? Yeah.
So for the last function, you want to plot different methods for this class, which method?
Which of the schemes should you use? So it depends. Usually, if you go into the minimize documentation, there should be a list of all those different schemes, right? And it will specify what some advantages and disadvantages of them are. For instance, I think FMIN, certain ones can handle on the optimization any kind of optimization problem. Other ones are more limited. Like they'll say this one can't handle constraints. Let's say say I want to find the minimum of this function. But I want to find the minimum that lies between here and here. Some of the methods can't handle that. You can't specify that I want it to be between here and there. It might end up with this minimum. But you want to specify this as a constraint. You can't do that with all of them. So it'll tell you certain ones can handle certain types of problems, certain ones can't.
On that note, why would we ever use, I guess, optimized off brute versus like basic options?
Because optimize alone is not guaranteed to work. It's a gradient-based method, and for large problems, it's going to be faster and more efficient, but it's not guaranteed to work. It could get stuck in a local minimum when you're trying to find a global one, or so brute will take a lot longer, and it's probably computationally feasible for 3D problems or above, but it is going to be more guaranteed to find something for you. So if you're dealing with a very simple problem in low number of dimensions, brute might be a way to go if other methods are failing you. Good question. Yeah.
Then what's the difference? Is it like, if like similar root, is that different than differences for actually?
I think brute and solve are basically the same.
But for the minimum one, like on minimize is more general, then would you ever want to use like the brute force one?
That's what she was just asking. Oh, so, okay, so.
There's a brute force, what are you talking about brute?
Well, there are like two global optimizers, the brute and base and hopping.
Yeah.
Brute and base and hopping.
Right, so,
It's the same idea.
right, so
Called,
one would always, or
Okay,
be more likely to find it.
so we're never going to use any of the brute force methods with base and hopping. We're not going to do global optimization in this class. I think base and hopping is probably going to try a bunch of different starting guesses. And then brute is actually going to enumerate like a bunch of possibilities and like check all of them. And you're asking the equivalent, not for minimize, but for,
yes,
for minimize. They're all the same idea. Why would you use them if the method itself, it's gradient based, is not working? So by default, fsolve and minimize are using gradient based methods. And so they're not guaranteed to find a solution or necessarily a global solution. If you want to find a particular, if you want to make sure that it works out, then you can use the brutes or the base and hopping, brute or base and hopping. For either, I don't know, I don't remember specifically what the options were for different ones, but yeah. See how, I don't know, my mind works because it associates these things. There's so many things that are similar about brute finding and minimization that I didn't really keep it straight, which is for Rich. Sorry about that. Yeah. You said, is it possible to view the polynomial that SymPy computes when you curve it?
No,
Interpolation?
yeah.
Yeah, what kind of object does it return?
It's a graph.
Well, that's what it's cubically curved.
Yeah.
Yeah, I'm sure that interp 1D, well, this is actually returned a function. So cubic interp is returned a function handle. I'm sure, actually, I don't know. Okay, so the question is interp 1D. All that we ended up doing was plotting the results, and it gave us some plot. And he says, what if I want to look at what defines this function? I don't know off the top of my head. You can look at the interp 1D documentation, and maybe there's some way of seeing coefficients or something. Let me take a look at that afterwards with you. But yeah, I've looked at the documentation. I don't know off the top of my head. Good question, though. Yeah.
For
let's do a simple curve fit example. Okay, so let's say that I draw something on the board. It looks something like that. This is all the data I've got. Excuse me, it's curve fitting, so I don't have that to begin with. I just have points. And you say, this looks like a parabola. So I am going to guess that, so these are my x and y points. These are my x and y points that I've got. So for each of these x's, I have a corresponding y value. So I've got two arrays, x and y, right? And I want to find a curve fit. So I know that I decide a priori that I want to fit a quadratic to this data. And a quadratic has three parameters that I don't know. So, you know, a, B, and C are the three things that I need. And so what it's going to do is it starts with a guess, and it says, all right, my guess makes a parabola that looks something like, maybe my guess parabola looks like this. It doesn't fit the data particularly well. Actually, maybe it's wider than that. Let's make it fit even worse. This is my original parabola from my guess. I guessed A, B, and C, and it produces this parabola. And then it says, all right, what's the error here? All right, what's the error here? What's the error here? What is the error at all these places? I'm going to compute how wrong my guess for A, B, and C was by looking and seeing what all these errors are, taking the square of all of them, adding them all together, and taking the square root again. And that gives me a single number, a single error, that tells me how bad my guess was. And the goal of curve fit is to try to minimize that error, to make that as small as it possibly can be, to find the value so it keeps on varying A, B, and C, to make that value as small as possible. So let's get back to the specifics to your question. Did that understanding what it's trying to do make sense?
Just depends on what kind of function.
So you have to specify, yeah, what kind of function it's going to be. And based on that, there's going to be certain variables that it can tweak in order to make it, to fit it best. But you have to decide the form of the function, yes. Did that answer your question? Okay.
Is that essentially like the same, it sounds like the same framework as like a linear regression model?
Yeah.
So can we do like a multivariate case when it still work?
I'm not sure if curve fit can do, but you can certainly do optimize. And that was kind of what I suggested you do, is try doing exactly the same thing curve fit does, but do it with optimize. Because we just explained what this optimization problem is. Calculates all the errors, squares them up, sums it, and that's the thing that it's trying to minimize. Express that in the terms of minimization. And so certainly you could do something, I mean, optimize, or minimize, opens up the possibility of doing anything you want, regardless of whether you can force curve fit to do it. So I don't really know. Yeah, you can take it from that. Yeah.
Can you also go over what gradient is?
Oh, you already have one. What is gradient descent? Sure. We can review that. That's in the videos. Did you watch the videos?
Yeah.
Okay. Do you want to talk about it for root finding or for minimization? Let's talk about it for root finding. All right, so we've got some parabola or some sort of function. It doesn't matter actually what that is. You want to find its root or where it passes 0. So this is here's the x-axis. Here's the y-axis. You want to find out this point. And all the numerical algorithms, you have to provide a guess. So I'm going to guess that this curve, this is my f of x, I'm going to guess that at x equals x naught, that my function crosses 0. But that's not true. It's wrong. It's just a guess. So what gradient descent says is, well, I'm wrong. How can I improve my guess? How can I change x naught? Which direction should I go? Should I add to it? So is that going to get me closer to where the function get goes to 0, or should I subtract from it? The way, and how much should I add or subtract from it? It says, regardless of what this is, as long as it's a reasonably well-behaved function, at least locally, at least very close. If you zoom in really close, this function, you zoom in really close, regardless of what function it is, it looks like a straight line. So let's assume it's a straight line and find out where that straight line crosses 0. So even if the math doesn't make sense of that, so I'll explain how to math it. We do it pretty quickly, but what it does is it approximates it a straight line. It says, I'm going to approximate this function as the tangent line at that point, and find out where that tangent line hits 0. That's my new guess. I'm going to do that same process multiple times, approximate the curve as the tangent line, find out where the tangent line hits 0, and that's my new guess. When I finally end up with a guess that produces an f of x that is less than some tolerance, or the absolute value is within some tolerance, I should say, as long as my f at my guess is small enough, is within some band of 0, that's when I'm going to stop. That's the very simplest form of gradient descent.
Why are these functions better than, let's say, making your own function and setting the derivative to 0 and then solving for the roots or?
Okay, so you're asking why is minimize better than if you wanted to minimize instead, take the derivative and solve for when it equals 0, right?
Yeah.
Why is it better? First of all, so in order to do that, presumably you'd use, say, fsolve instead to find the root. The thing with minimize is that it will make sure that it's a minimum, not a maximum. That's the simplest thing. That's the first improvement. It will make sure for you that it's heading towards a minimum and not just where the derivative is 0. Because where the derivative is 0 could be a minimum, maximum, or in multiple dimensions a saddle point. And so it makes sure it finds your minimum. The other thing that it does is it handles some additional things that root finding doesn't. You can start adding constraints, like I said before. If I have something where I know it's got multiple local minima, but I want this one, I can specify, I want you to lie within here. Or in multiple dimensions, you can start specifying nonlinear constraints, saying if it's in 3 dimensions, I want to make sure it's within this spheres in 3D space. I only want you to consider this region. You can't do that with fsolve. So there's a lot of additional flexibility. And so I would say the better question is, instead of, why not just use minimize instead of using fsolve? Use minimize to find where you minimize the absolute value of the function. Minimize is more general than fsolve, I would say. But sometimes you trade off efficiency for generality. So you make minimize more general, but it's a little less efficient for this particular problem than fsolve is. So that answer your question?
Yeah.
Okay. Likewise, you wouldn't want to use fsolve to solve a linear problem, because there's a lot faster techniques for linear problems. So again, fsolve is more general, but linear techniques are faster if you have a linear problem. That's a common theme in scientific computing. Use the algorithm that's appropriate for the particular job. Use the most specific one you can. It's probably going to be what I use. Others? Yeah.
For interpolation, when it actually specifies, is the default for both 1D and 2D both linear?
When it specifies the type of interpolation, is the default linear? That is a question that I have not memorized, but can you not find it in the documentation?
I couldn't see it for 2D.
Oh, for 2D, is there a separate 2D function? I can't remember.
For feature 2D.
Okay, if it's not in the documentation, I would maybe test it out and figure it out. I don't know. Yeah?
Oh, what is like the EIS variable, the EF variable?
The disk variable in VFGS. So sometimes when it's going through those internal calculations, sometimes you want it to just give you the final result. Sometimes you want it to tell you what's going on. Because, for instance, when I was doing my thesis, I had programs that did minimization that lasted all day. You know, they'd run for an hour. You want to see where it is. Are you making any progress at all, or is my computer just crunching numbers and give me some indication of what's going on? Kind of like a status bar. So you can use that disk message or variable to specify how much detail do you want to print out to the console. Yeah. Others? Okay. 12:20. I think I'm only giving you 3 minutes for this quiz. It's quite short. You'll either know the answers, you won't. We'll finish at 12:24. And the password is optimal control with a space. The reason that I worked on optimal control, and that deals with those numerical stuff, deals with minimization. Who's still working? Everybody still around with this? Okay, so end time 12:23. If I see your thing is submitted afterwards, then it's not going to count. So make sure that you know. Okay, so I wanted to just talk about a brief point in the quiz. If you missed the part about what you have to specify for either of those functions, you have to specify the function and a guess. How does it figure out what the derivative is? And you know, for the minimization, it has to know what the second derivative is as well. But you saw in the assignment or the preparation, when you used it, all you had to specify was the function itself, not its derivative or its second derivative. What it does is it approximates those derivatives. It says, all right, if my function looks like this, all I need, I don't need the derivative of the function anywhere. I only need the derivative around the guess. So if this is where my guess was, Well, take a look a little bit to the right of it, take a look to the left of it, and calculate the slope between them. That's a good approximation of the derivative at this particular point. And you can do that and get second derivatives as well. Same sort of idea. So even though it needs for the algorithm to work the derivative and the second derivative, you don't need to specify those when you're doing minimization of cycles, because it approximates this for you. Now sometimes in more advanced applications that can cause problems because there's error. And it's actually can be pretty bad. If you don't get good derivatives, you can have big problems. So I'm kind of a nerd and interested in how to approximate derivatives. There's all kinds of cool things you can do. It turns out there's programs that you can write that take the derivative of code that you can write. It's kind of weird, right? You write a function in code, even though it's not symbols in math, it represents something that you could write with math symbols, right? It turns out that there's code that can differentiate out of code. And so that's one really good way to get exact derivatives. Much better than this approximation here. But that's not what sci-fi is doing, so we don't talk about it. All kinds of other cool ideas. Apparently there's a complex step. I said, I'm going to look a little bit over to the right, I'm going to look a little bit over to the left. It's kind of a mind bender, but what if I take a small step in the complex direction? I add a little bit of an imaginary component to it. Turns out you can get approximate derivatives better for certain functions that way. Higher order methods, I don't just look at 2 points, I look at multiple points. All right, I'm going to shut up. The thing that I just talked about, automatic or algorithmic differentiation, where a code differentiates another code. Does it give an exact? Numerically exact, I should say. But this approximation is not only exact, it's wrong not only because of numerical problems, it's because you're approximating the derivative by looking a little bit out to the right and a little bit out to the left. That's wrong. The slope between those 2 points is not the same as the derivative. Numerically, that's one way to do it, but there's other. I'm saying there's other ways. You could take multiple points. Look, I mean, one way we could do it is by saying, let's look at just the point to the right of it, and let's look at the original point itself. What is the slope between those 2? That's first order accurate. If you look at the point to the left and the point to the right, that's going to become second order accurate, etc. So there's different approximation methods with numbers. It's a very big subject. But SciPy does some smart things automatically for you. Other questions before we get started on the assignment? I was also thinking that during this discussion, I could take a look at the, I could look at the preparation from last time. So if you want to listen, go ahead and pay attention, and I'll walk you through my preparation document. Does that sound good? Who would be interested in watching me go through my preparation for this assignment? 1, 2, 3, 4. Not so many. Maybe what I'll do is I'll do it in discussion tomorrow instead. How about that? Maybe that's what I'll end up doing in discussion. So I'll let you guys get started on the actual assignment. If you have questions on how to set it up, that's the hardest thing, is figuring out how to turn this problem into a numerical problem. And I know it's a lot to handle to begin with, so ask questions. Call me over. I'm going to turn this off first.